Hello, hello. I hope you can hear me, see me. Yeah, I see some GMs. Yeah, quickly do some, please, GMs in the chat so I can know you can hear me. And then we can easily start with this workshop. I hope it's not too early. Are we gonna use Brownie / Hardhat for pure solidity? No, actually today there will be no code along whatsoever. We are going to cover basics about smart contract security in general. We're going to discuss about some common vulnerabilities. So any framework in theory is applicable, but we are not going to code anything. Only the ability to read Solidity is enough for this workshop. I'll cover a lot of testing tools, frameworks, common attacks, common defense to that attacks, and also some auditing techniques and best practices. So it's going to be approximately hour and a half workshop, but not code along. So grab a coffee, maybe you're going to take some notes, whatever, and basically enjoy this workshop. Cool, I can see some GMs in the chat. We are right on time, so I think we can start, yeah. So welcome to another Chainlink Spring 2022 Hackathon workshop. Today, our topic is a bit more advanced. We're going to cover smart contract security and auditing 101. There will be another workshop called Smart Contract Security and Auditing 201, which is going to be the next chapter of today's talk. Patrick Owens will probably host that workshop. Today, I will be your main host. So my name is, once again, Andrei Rakic. I'm one of the developer advocates for Chainlink Protocol at Chainlink Labs. You can see here my Twitter handle listed, also my email. Feel free to reach me out on Twitter. It's the best, I think, to talk and discuss anything Chainlink related or smart contract security or auditing related. So let's start with the quick agenda. As I said today, there is not going to be code along whatsoever. We are just going to read a lot of Solidity and discuss it. Feel free to write in the chat whenever you have some questions. It will be much easier for me today to follow up on your questions and answer them, because I want basically do any coding, so I can focus on two monitors. So in approximately hour and a half, we're going to cover what I called road to audit. That basically means if you are a smart contract developer, what you can do before the final audit step. So audit is basically when you pay to some company or individual to do a security review of your code before you ship it, deployed to some Java purpose blockchain. Then we are going to cover some common vulnerabilities. What I mean by that, we are going to discuss, I'll basically show you some common vulnerability contracts. Then I will show you how you can attack them. And finally, I'll show you how you can defend and prevent those attacks to happen to you. Then I'll cover some best practices. We'll have 20 plus best practices. Also, there basically you don't need to trust me that those are like best practices. It's basically because of some other vulnerabilities, but we don't have probably time to cover all of them. So I'll just say something like use TX origin instead of message.sender, and I'll explain you why, but we're not going to cover in this section like the Solidity code snippet of that attack as well. And finally, we'll cover some auditing techniques. So once your contract reaches the auditing phase, there are several types of audits. There are several techniques, tools, which auditing companies use on a daily basis. So basically, I will try to show you how basically the work of one smart contract security auditor, for example, looks like. Maybe that's something you are interested in and you want to pursue your career in that direction. So let's dive in. So first, road to audit. As I said, imagine that you're a smart contract developer or a part of smart contract development team. What you can do before the final step, which is audit, of course. So the most common thing is testing. So basically, when you're developing your smart contracts, around 75% to to 80% of your time will go to testing. And that's like really important step. So development of smart contracts aside, the testing is the most important thing in smart contract development in general. And why is that? Because if you think about it, essentially programming smart contracts is more like programming hardware than programming software because of the nature of the blockchain technology itself. So basically, we all know that after we deploy our smart contract, to some general purpose blockchain, it can be testnet as well. We cannot change that smart contract whatsoever. It is live. Everyone can see your source code, modify it or delete it in any way. Basically, if you want to update it, you need to deploy a new instance, or you need to upgrade your smart contract. There was several workshops on that topic during this hackathon about proxy upgradability patterns, some other upgradability patterns, and so on and so forth. But basically, when you're like deploying the new instance of a contract, but basically you cannot change a single line of the smart contract when it is deployed to some blockchain, right? So that's why testing is so important. Imagine that you're building a rocket and you need to ship that rocket to the space, for example, to the International Space Station or to the Moon or to the Mars or to some other planet. When the rocket ships from the planet Earth, there's no patches, there's no fixes, nothing. So it will either go to the space successfully or it will go down into the ocean or something like that. So it's similar with the smart contracts. So that's why test-driven development is your friend. That's basically a technique where you first write your tests, which fails, of course, and then you write the implementation of smart contract to pass those tests. So basically build, test, repeat. That will be your main flow. Okay, so after the successful testing and final development, there's like that final step which called audit. So basically auditing is when you pay some auditing company or some individuals to do a security check of your set of smart contracts. But as you can see on this slide, and I cannot stress this hard enough, the audited code doesn't necessarily mean secured code. And any audited company will tell you the same. So audited code is not equal to secure code, because auditing or audit process cannot patch zero-day vulnerabilities because they cannot imagine what can happen in the future. So as Dijkstra said on this quote, program testing can be used to show the presence of bugs, but never to show their absence. So keep this in mind, that even with the audit, your smart contract is probably not 100% secure. And you need to adapt to even the changes of the initial blockchain itself, not just the your source code. Okay, so common smart contract development path is something like this. So step 0, I haven't wrote it here on the slide, is basically the development of some smart contract. So either in Solidity or Viper or Rust or whatever smart contract language, you need to develop your smart contracts. Then, as I said, like 75% to 80% of your time will go to testing. And there are several different testing strategies. There are several different types of tests. I will cover all of them in the next slide. But basically, the testing is the most important one. Then we have, after the successful tests, then we have something called gas and memory optimizations, because the gas is currently expensive. Not expensive, but it's not cheap. Basically, you need to pay for some computation on any blockchain. You tend to optimize your code in terms of gas or logic, and also in terms of memory. So maybe prepack your storage variables or something like that. But don't get trapped to make useless optimizations. For example, if you're going to save some 20 units of gas with some assembly code snippet or rearranging your code, please don't do that, because it can, in some cases, result in unexpected side effects, and that's we want to avoid. Then code coverage. So if you watched testing with Hardhead workshop, we covered code coverage. Basically, it's a measure of percent of smart contract, your Solidity file or whatever Viper Rust file covered with tests. So basically, when you write a test, you're going to increase that percentage because you covered some part of your smart contract with tests. In an ideal world, you want to have 100% of coverage, but that's not always can be the case. And don't get entrapped to reach that famous 100%, because maybe you'll change some of your test implementation or some slightly change in smart contract implementation, and again, that can result in side effects. So if you have above 90% of code coverage, you're good to go, basically. Then documentation. I know all of our developers are kind of bored to write documentation, but it's really important because auditing firm and also like your users can read and understand your code. NAT spec is really important, so make sure to write your NAT spec in Solidity. NAT spec is basically a set of comments which describe the code itself with specific keywords. You can find it on the official documentation and on Solidity documentation, and basically documentation is important. Then we have peer review. Basically, you're going to work in some team. Don't hesitate to ask your colleagues to review your code for yourself. Basically, that's kind of like a common practice in bigger teams, that one or some group of individuals will implement some feature, and then the other team members will take a look of that implementation, comment it, review it, etc. And then after all of those checks, finally you're going to merge your PR into the main branch or dev branch. And we have two optional steps, which is static analysis and symbolic execution. We'll cover those later in the auditing techniques, but basically static analysis is when you run a tool to statically go through your source code without implementing it. So maybe static analyzer will find a string that you're using TX origin in your smart contract without knowing why. And it's going to warn you, hey, you're using TX origin, maybe that's not the safest way. But if you know what you're doing, you can proceed with that, or you can just have that aha moment and say, hey, I need to refactor this to use message.sender. Symbolic execution is basically a set of common state changes in some mathematical language to try to basically find a correctness of your smart contract in like a symbolic way. I will cover that later. And also final step is, of course, audit. So a bit more of tests. There are different kinds of tests. There's four main type of tests, and this is like the most common pattern nowadays for testing smart contracts. So we have unit tests, integrational tests, end-to-end tests, and property-based tests or fuzz tests. Unit test is basically when you have a local blockchain. Imagine that you're writing your test in Hardhat. You have like a local Hardhat node. In Truffle, you have a Ganache. Brown, you have also like a local node. And you're going to deploy only one instance of your smart contracts, and all of the rest will be mocks. So basically, mocking is a technique where you write a mock contract that says something like, whatever, this contract should interact with my main contract, which I'm testing. Whatever you're doing, just return this value. So it can be return 18 decimals for like mock ERC20 token, or you can specify it to transfer from function to always return true, because you don't care about testing the transfer from function or ERC20 token. At that point, you just care of testing your own implementation of smart contract. Then we have integrational tests, where pretty much the same story, but you also have local blockchain, but not mocks. So you will now deploy all of your smart contracts, and you're going to test your whole flow now. So imagine that again, you have like a smart contract which need to transfer some ERC20 token. And inside the unit test for ERC20 token, you test the transfer function. Inside your main contract, you have tested that main function, which is called transfers, whatever. And because you have mocks, everything worked. But now with integrational tests, you test the whole flow, and you'll encounter the exception because you'll probably need to approve first spending, and then like to call transfer from a function. So this is like the testing the whole flow. End-to-end tests are similar to integrational tests, but you're not doing it on local blockchain. You're doing it on mainnet fork. So that's a really powerful technique where you basically test or upon some state in particular block on some general purpose blockchain using probably alchemy keys. And property path test or fast testing, we'll cover them later. It's a common technique where basically the built-in fuzzer, Foundry has a built-in fuzzer, try to break your implementation of smart contract. You write those tests in Solidity because it's going to generate random inputs for your function in order to break it basically. So let's start now with some more interesting topics, and that's common vulnerabilities. Okay, so about the common vulnerabilities, in this section, we are going to cover some common vulnerable contracts. I'm going to show you how you can attack them, and then I'll show you how you can defend your smart contracts from those attacks. Let me see. We have a question. Can you test Chainlink VRF v2 without using mocks, just using integrational tests? No. Basically, if you want to write unit tests for your VRF v2, you will use a mock from the official repo. For integrational tests, you still need to mock it in some way because it's on local blockchain. The hacky way is basically to host your Chainlink node in localhost and then to communicate with this node, but basically you will need to run a mainnet fork, and then you can just specify the block after the VRF v2 is deployed, and then you can test with that. Okay, let's continue after this question. So the first and the most common vulnerability is reentrancy, and this is so common, but still, like, a lot of projects get wrecked or hacked because of reentrancy attacks. So basically, let's take a look at this vulnerable contract. The contract name is Staker. Basically, you can deposit some native coins, Ether or some other native coins, for example, Matic and Polygon, into this smart contract, and then like this smart contract will do something with that crypto, whatever, and then you'll have the ability to withdraw your portion from this contract whenever you want, basically. So there's like a public mapping balances, which track basically address is like a key of your wallet, EOA, and UINT256 is basically amount of how many like coins you deposit into the contract itself. And if you take a look at the withdrawal function, so we have some required that this amount that you want to withdraw need to be, actually this is a mistake, need to be less than balances of the message.sender. Sorry, that's an unintentional bug. But if you take a look down here, we have a transfer of ethers or native coins to the message.sender, and after that we update this mapping storage variable. So this is bad because you can attack this contract like this. So this is an attacker contract. So basically, you'll have this staker instance, and you have this attack function. So you can deposit some value, some amount of coins, calling deposit function, and then call withdraw function. And if we go back slightly to this vulnerable contract, when we call withdraw, we first send the coins to the message.sender and then update the storage variable. So when your smart contract, because it can receive ethers or native coins if you implement fallback function. So once you call your fallback function will be triggered when you receive the coins. Then you have this condition when if the balance of the staker contract is greater than 0, you want to withdraw more. And because of that, another transaction, staker contract will not have time to update this storage variable to this minus equal amount, and then you can still withdraw basically all of the remained ether from the staker contract. You can basically drain it out because of the reentrancy bug. So how you can defend? So basically, first you need to update the storage variable to perform any logic inside the withdraw function, and then finally to call the outside uh, contract to perform these transfers. So you need to send coins at the very last step. The other common technique is basically to use Open Settlements Reentrancy Guard. That's a library which has this non-reentrant modifier. Basically, it will create a mutex, so you cannot enter the withdraw function until its very end, so you're pretty much safe. Or you can implement your own reentrancy modifier. It's pretty simple, but in theory, your withdrawal function should look like this. So you have this non-reentrant modifier, and you update the storage variable first, and then transfer the coins itself. Okay, vulnerability number 2, on-chain randomness. So there's a common thing still that not many, but some of the projects will still use on-chain randomness for some gambling contracts or some crypto giveaways contracts or whatsoever. And those contracts will implement randomness using either block timestamp or block number or block hash or something like this. And the problem with this implementation, so if you look at this coin flip contract, basically we have this flip function, which only take one parameter and it's guess, which is true false. So you have 50-50 chance to guess the flip. And you basically has this consecutive wins. Your goal is to have, for example, let's say 10 consecutive wins, and then you can get the price, maybe 32 ethers, for example. And there's like an implementation of this on-chain randomness. The problem with this approach is that this is pseudo randomness. So miners can manipulate with this information in a way that they can know block timestamp, or not know, but calculate block timestamp in advance or block number, and then they can, because they can see how you use those parameters to calculate randomness, they can predict your randomness before it really actually happens. And that's a problem. So pseudo randomness is there in many languages. For example, in JavaScript, if you type math.random, you'll have receive pseudo random number, not the pure random value, and it's the same with the solidity. We have a question, sorry. Can you explain the syntax of the last line? Oh yeah, so this is a Turner operator. Basically, if side equals guess, then consecutive wins plus plus, else consecutive wins 0. So it's the same syntax as if else branch, just it's easier to write it in one line, and I did it because of the space on the slide. If you have like a giant if else block, it will be much harder to read. It's because of the size of the font, basically. So it's still the same, like if side equals guess, then consecutive is plus plus, else consecutive is equals 0. Okay, so how we can prevent from on-chain randomness attack? So don't rely on block hash or block timestamp or block.number as a source of randomness. This is bad because miners can calculate and predict those values. Instead, the safest way and the only right way is to use Chainlink VRF, because Chainlink VRF will provide you the true random values which you can cryptographically verify. Vulnerability number 3, overflow underflow. So this is a really common vulnerability, even from the start of the Solidity itself. And still, I see that some projects get wrecked because of this. So basically, overflow, in terms of computer science, is when you run out of bits to the left. So imagine that you perform addition of 2-bit values, so 01001 plus 10001. So overflow is when you run out the bits on the left, so it's magnitude, And underflow is when you run out of the bits to the right, it's precision, so with division. So if we have uint8 values, so uint8 can grab portion from 0 to 255. So this is the range, 0 to 255. If you type uint8, the name of the variable, equal 256, you will have the error from the Solidity compiler. And basically when you, if you have overflow, basically when you type 255 plus 1, the result is not 256, the result is 0 because we're at the beginning. The same applies to 0 minus 1 is 255, so these both examples are overflows, and the underflow is, as I said, precision, so 3 divided by 2 is not 1, is 0 point something, but because we have integers and the solidity, it's going to underflow. And this is bad because maybe you want to calculate some amount of tokens you received from some prices, sorry, you received from Chainlink price feed, and maybe you need to do some calculation. And if you have hit underflows or overflows, you're in risk to get wrecked. So this is a vulnerable contract. Notice the version of the solidity is 0.7. Basically, we have this staker function contract. Sorry. So there's a struct stake info with amount you staked and the value in seconds, which that stake is locked until. So block timestamp plus some amount is, for example, you're locked this token for 3 months. And there's like a stake function, which is payable, so just locking. And then maybe you want to increase your lock time even more because it's not good for you to withdraw to unstake tokens right now because the price went down whatsoever. And you can do it. You just pass seconds to increase. And look that we are using plus equal, just simple plus. And then unstake, basically, the main require here is that block's timestamp is greater than a locked until. And after that, we have some implementation of unstaking. That's not important. So if you take a look at this increase lock time, you can see how you can increase by just plus equal your locked until time. And then in the unstake function, take a look at this require statement that the current block timestamp needs to be greater than this locked until. And in theory, it can't be after the time has passed because like when you stake, you use block timestamp plus some stake period, and you cannot revert back in time. But you can attack this contract if you're using Solidity versions under 0.8. If you take a look at this attack function. So a stake is just to stake some initial tokens, and then with attack, you call inside the attack function, you call increase lock time, and you're increasing by uint max. So if we have, so for uint 256, it's a giant number, but with uint 8, it will be 255 plus 1 minus the current locked until. And this is a simple math. If you do it on your phone or calculator, you can see that the result is 0. And then basically you can unstake tokens because block timestamp will be greater than 0. So how you can prevent overflow and underflow attacks? Basically, if you're using Solidity versions less than 0.8, the mandatory step is to use safe math libraries. So safe math is common library embedded into Open Sapiens contracts, so make sure to use it. If you're from Solidity 0.8 and above, the good news are that Solidity integrates safe math natively. So basically, you don't need to worry about this anymore because the exact same contract we wrote over there, if you change the Solidity version to beyond or above 0.8 instead of 0.7, will work properly. So just take this in mind. Okay, fourth and final common vulnerability are so-called price oracle attacks. So I wrote the simplest DEX ever here. It has only one liquidity pair, so we have two storage variables, token 1 and token 2, their addresses, And there's like add liquidity function on the bottom, which basically just add liquidity to this DEX, simple as X ever. And there is like swap function, which at some point needs get swap price. So get swap price is a view function, which basically returns the price by amount. You multiply that amount with the balance of the destination token in the DEX and divide that value with the balance of the front token. And you'll have some price, right? Imagine now that you're building for this hackathon some DeFi protocol on top of this, my vulnerable simple DEX, and you want to use this get swap price basically to calculate the price of some tokens, right? This is bad idea because you can manipulate this price either by adding enormous liquidity to one side of the pool, where you're basically going to disproper the price itself, or by doing consecutive swaps until you drain out one side of the liquidity. And then the price will be something like 0, 1, or whatsoever. But even if you don't dry the whole portion, the price will be inaccurate, right? So what you can do? So first of all, don't ever use low liquidity tokens. So some tokens that are not too famous, has not great liquidity, avoid them. Simply avoid them. Has like a mandate that you have like a list of tokens that is supported on your protocol, and that's it. This is the safest bet. Then when you use DEX as a source of price oracle, basically the name of those oracles are TWAP, time-weighted average price oracles. And you need to be really, really, really careful with TWAP oracles because they can be pretty easily manipulated, even if they're not vulnerable like my DEX. Still, the same techniques applies there with flash loans attacks, whatever. You're not going to get the actual price at some point, and this is bad. So if you want to use these TWAP oracles, I don't recommend you to do that. But if you want, you need to be really, really careful, and you need to know exactly what you're doing if you want to be avoid to get wrecked. So a lot of different checks you need to implement, and so on and so forth. And there's a lot of projects still today which gets wrecked and hacked because of the TWAP oracles. And another thing which is not too bad with these TWAP oracles is basically the DEX is still a centralized price oracle. So don't ever use a single price oracle or single data source when it comes to prices. So even if the best DEX is your source of price truth, let's say, it's still one entity, a centralized price oracle. So the better idea, and I think the only one possible, is to use Chainlink price fits, because Chainlink price fits will you provide using aggregational algorithm the most accurate, or actually the real price of any asset, because basically the price is determined by the market, and if you have several different sources, a lot of taxes, DeFi protocols whatsoever, then you can combine all of those values and calculate it using price fits algorithm to get the actual price, right? So let's now start with some best practices. So I covered some of the common vulnerabilities, and I show you how you can defend them, like use Solidity 0.8, or use SafeMath, or use Reentrancy Guard, or use price feeds, or use VRF, and so on. There's a lot of other common hacks and vulnerabilities, and we don't have time to explain them all, but I collected some best practices, so some solutions to those vulnerabilities or hacks. Some solutions applies to several different hacks, so that's even better. So try to follow those practices or recommendations during your development flow. It will going to be your smart contract will be much safer if you follow those practices. So let's start with the first out of 7 slides for best practices. The first one is to monitor and upgrade package JSON dependencies. So GitHub has built-in dependency bot, which will email you or trigger you when some vulnerability, high severity or medium severity or even low severity, is found at some version of some package. And if you use that version of that package in some of your repos, it will basically alarm you to upgrade. And most of the devs actually do this when the GitHub alarms them, or when they want to upgrade because of the new features. But the thing is that you should monitor and upgrade this dependency regularly, even if there's no vulnerabilities, because with the latest or almost latest version, you're assured that they're like much more secure than the previous ones, because they're actively maintained by the teams who is basically building them. Then number 2, use stable Solidity versions. So Solidity is also a language that involves, and there's like several Solidity versions, included several patches, new features, fixing vulnerabilities, fixing bugs, and so on and so forth. So this is a list of some of the stable Solidity versions. So 0.5.16, 0.5 for 17, then 0.6. 6.18, 6.11, 6.12, 7.5, 7.6, and 8.4. So this is like the safest bet. If you're compiling with your Hardhead or Brownie project or Truffle or Foundry with these Solidity versions, you're pretty much safe. Also, this is a low severity issue, but avoid floating pragma. So basically, if you type something like pragma Solidity version above 0.7 or 0.7 until 0.8.5 or whatever, you have a wide range of Solidity versions included. This is a low severity, but basically, if you test your set of smart contracts with one version and then you deploy with another, or you build on top of that with another version, it will compile, but you're at risk to encounter some hidden vulnerability over there. So yeah, be careful about it. Then use check effects interactions pattern. So basically, this pattern means that you're going to first do a checks. Why isn't 0.6? Sorry. Probably I have the outdated data for 0.8.7. I wasn't so sure is it still stable. So that's basically why. Sorry about it. Yeah. So check effects interactions pattern. So basically, when you're writing your smart contract function, you first want to check with either require statements or modifiers that inputs are correct. So maybe only owner can call this function, or the input amount needs to be greater than 0 or whatsoever. Then you need to implement custom logic. So update storage variables, emit some events, something like that. And then finally, you need to call another contract. Or call another contract like swap or transfer some ethers or coins. And that's like the final step. That's how you can avoid reentrancy attack. Then take warning seriously. So this is from the official Solidity talks. Basically, if there's even a warning, try to analyze that warning, or maybe if you can slightly modify your implementation, you will remove that warning. And basically on the Solidity talks, they said that there's a reason for every warning, so maybe it can lead to some bug in the future. Okay, we have 2 questions. I will stop to answer them. So can we connect on Twitter or LinkedIn? Yes, David. So Andre_dev is my Twitter handle. Feel free to add me there. Could you explain TWAP Oracle manipulation attacks a bit more, or point to some resources? There are several resources on blog.chain.link. Maybe try to search them. It's basically analyzing of the performance of price feeds and TWAP oracles in general. Basically, the problem with TWAP oracles is that basically a single source of truth and can be easily manipulated. Also, if you go to Patrick's Twitter, there's this really good thread, I think 2 days ago. I retweeted as well, so maybe try it on my Twitter, so Andre_dev. There's like a giant thread on comparison between TWAP oracles and price fit. So yeah, either blog.chain.link or Twitter, or I think we have some videos on Chainlink YouTube as well. Okay, so next, keep it small and modular. Basically, you should tend to have your smart contracts small, and you can maybe divide them into some libraries or whatever, because it's easier to monitor them and to properly test them when you split some logic into several Solidity files instead of one giant file. KISS is a common term in computer science, not just for Solidity or Viper or smart contract development in general. Basically, you try to keep it as simple as possible, and that's how you can avoid bugs. Okay, next one. Always protect withdrawal functions. So if you go to SVC register and under 105 number, you can find this vulnerability. Basically, you want to always protect your withdrawal functions in a way that only admin or DAO can withdraw funds. So who can withdraw funds? What if some unexpected ether comes to your smart contract? Do you have mechanisms to do that? Also, if you have a smart contract but don't have like a function to withdraw ERC20 tokens, they're kind of locked there forever. So you need to take care of this. Another question. I want to work in security, blockchain, smart contracts. Do I need JavaScript and dev background? In theory, no, but it will be much easier to you to understand some concepts because you're familiar with those languages. But we'll cover some auditing techniques later in upcoming slides, so you will see some tools that auditors use on a daily basis. And then you can maybe Google them and explore them more. But basically, the most important skill is to understand how you can read smart contracts. What is SVC 105? Basically, SVC is the register with all of the common hacks and vulnerabilities. So 105 is basically a number for this particular vulnerability, kind of like ape and number. So it's a giant list. You can Google it, or I can post a link on my Twitter later with all of those, all of these vulnerabilities. But if you want to read more about this specific, just find it out under 105 number. That's it. Okay, next up, avoid self-destruct. So self-destruct is a built-in type keyword, which basically destructs your smart contract. How it can do it? So it will basically initiate all of the storage variables to their default values. So uint values will be 0, strings will be empty strings, booleans will be false. All of the locked ether or coins will be transferred to the address calling self-destruct, and if some other EOA tries to interact with your functions after self-destruct, they will basically encounter into revert transactions. So this is bad, and there's some I think there's some discussion about either actually removing this opcode in general from the EVM because you can. There's a hacky way where you can pre-compute your smart contract address with create2 and deploy it, and then you can self-destruct that instance and deploy another one with the same address, because you can again pre-compute it with create2 and you have like the salt, and then your users maybe cannot be aware that the change happened, and then you can perform an exit scan. So yeah, the safest way is basically to avoid self-destruct. Another question: are multi-sigs more secure or more vulnerable? They're more secure. So in theory, multi-sigs are much more secure than one admin wallet or whatsoever, because there are like several keys that need to be compromised in order to the whole vault to be compromised. So they're more secure, and use them, of course. Okay, so another one: modifiers shouldn't update state. So modifiers are really common in the smart contract development, basically to perform some require statement or to return true or false, but never ever modifiers shouldn't update state. So no logic inside the modifiers, please, because it's first, it's a really hacky way. Second, it's really hard to track them because the modifiers are at the top of your smart contract, and then you are using it in the functions down below. So maybe auditors will not see some problem because there's no code in front of their eyes. And also, like, this is really hacky if you update state because it cannot be applied to all functions. So, and that's not the main purpose of modifiers. Modifiers are just there to save you time on testing inputs, to not duplicate your code, and just use it for that, please. Okay. Yeah, some discussion about Multisig Wallet. Yeah, this is actually a good comment. Yeah, if you're using salt version under 0.8, use SafeMat, we covered that. Use Reentrancy Guard, we covered that as well. So this is to protect you from reentrancy attacks. We actually saw how you can attack some reentrance vulnerable contract using reentrancy. So use Reentrancy Guard. This is a modifier from OpenZeppelin's library. Then about sending Ether or any native coins. So this will be Matic for Polygon. From 2019, the only recommended way to send coins is using call and not transfer or send. So please avoid transfer and send because they're vulnerable. Just send ETH via call. And here you can see a simple code snippet how you can do it. It's pretty simple, pretty straightforward. So send tokens, send coins, sorry, native coins, ETH, using this way. That's it. Another one, avoid pseudo randomness. So we talked about pseudo randomness a lot. The solution is to use Chainlink VRF. You can also read a lot more about pseudo randomness attacks and hacks on, again, SVC register. This time the number for this hack is 120. So yeah, search for that and you could see like a giant text about pseudo randomness. The most secure way and the only right way essentially is to use Chainlink VRF. Then avoid TX origin, use message.sender. So if you want to do some authorization check, use message.sender, not TX origin, please. Because if you have like a middleman contract, so there's like a target contract, and when you call it from your wallet, message.sender is your wallet address. But if you deploy a middleman contract with some custom logic, which also like its intent is to hack the main contract and call the function of the main contract from your middleware contract, message.sender will be your middleware contract, and TX origin will be your wallet address. And basically, this if you're using TX origin for authorization, message sender or middleware contract can perform some hacks. So avoid TX origin, use message.sender. Next up, divide before multiply. Sorry. So if you do some number and multiply them by 1,000, and then divide that number by 5,000, and it's the same in a math way if you like first divide that number and then multiply it. So this is a code snippet you should follow along. So first multiplication, then divide, because if you first do a division, you're at risk to reach the underflow, which we talk about. And this is a common way to calculate percentages on a smart contract using basis point, basically. Another one, and this is really important. Basically, this applies to ERC20 tokens. When you call a proof function on your ERC20 token for your contract, for your tokens, and you basically approve some contract to spend, let's say, 1,000 of tokens, and you do a swap, and it doesn't spend all of those, or it does. Once you approve them again, then the number of tokens which this contract can use or spend is greater than that initial value, because in theory you should need to call approve with some number, then to call approve with 0 to decrease allowance, and then to call approve. So we pretty much always forget to do that. So OpenSupplement implemented this two additional methods. They're not part of the main ERC20 standard, but basically you can implement by your own. Increase allowance and decrease allowance are basically going to combine this approve 0 and approve to another value. So please use them. They're much more secure. Always check for address 0. This is a black hole address where you basically, this is the way to burn your tokens. If you send them to that address, you cannot retrieve them because there's no private key for address 0. You need to add some additional checks, probably in your modifiers, that the amount or is not 0, or the destination address is not 0, or the contract address is not 0, or something like that, because maybe your front end or UI will not parse some parameter and input, and it will pass the 0 value, and then you're basically got wrecked. So this is a simple check to perform. Just don't forget to check for address 0. We're almost done. Yeah, another one. Always test the extreme case of external integrations. So if you're using Uniswap to perform some swaps inside your greater DeFi project, is it possible that Uniswap run out of liquidity for some tokens? Yes, it's possible. So what's going to happen to your contract in that case? Do you actually have some implementation? Do you have some cards for that? Test that scenario. So basically, as I said, 80% of your time will go to testing. And testing of these extreme edge cases will be part of that. Basically, if you are using some L2, some Arbitrum or Optimism chain whatsoever, that have some so-called sequencers, can that sequencer go down? Yes. What's your contract will do that in that extreme case of Black Swan event? Test that case. Pretty simple. Yeah, please can you explain more on the approve, and please give an example? I didn't understand. Yeah. So if you have ERC20 token and you have 1,000 of those tokens, and there's like some DEX. To do a swap, you need to approve, for example, 500 of tokens to be consumed by the DEX smart contract, and it will consume it. But inside the token contract itself, the approval for that DEX will still be 500. And you want to be a 0, because after the swap is initiated, you don't want to give the opportunity to that DEX to spend more of your tokens. But if you forgot to call after the swap approve 0, in theory, if somehow you mistakenly call the swap function again, it can again spend the another 500 of amount of your tokens, because the approval is still 500, right? So you need to go call approve 0, but that's like not so common. So increase and decrease allowance is much more simpler, because it will combine those two calls. So this is a code snippets from OpenZeppelin. So that's why, to avoid mistakenly lose your coins or tokens because you haven't called approve 0 after the usage from the external contract. Okay, next up, mainnet forking. So this is really important. Again, if you want to properly test your contracts, you need to fork and test it on the real environment. Local blockchains are good, great, but this is not the real thing. So try to test it on a real environment with other protocols. Also, as part of your test, you need to go to testnets, but they're not like the exact copies of the mainnets, unfortunately. So once again, this is better. Yeah, don't make useless optimization. Security is top priority. I already said that. So basically, once you're finished with your testing process, we'll try probably to optimize something in terms of gas consumption, in terms of memory, and maybe you will rearrange your storage variables, or you'll slightly change your implementation of smart contract or of your function, pardon, or maybe you can open an assembly, code brackets whatsoever. And the thing is that if the optimization is too low, maybe for 20 or 30 gas units, and you're using assembly instead of a regular Solidity, maybe that's not a good idea if you don't know what you're doing exactly, because it can, in theory, result in some side effects. So don't make useless optimizations. Make optimizations, of course, in terms of gas, in terms of memory, all the time, but don't make useless because security is still /1 priority. And final best practices is basically applies to you working in a team. You'll probably implement some CI/CD flow to block merging PRs if all of the tests are not successful. So run test suite on each PR or push and mandate that all of them are green, they're passed. Also mandate greater code coverage greater than 90% for that specific functionality. Mandate that the code is properly formatted using linter. Also, this implies to NutSpec as well, because if you're using NutSpec, then after the deployment, there's several hardhat plugins which can generate the documentation in one single command, using one single command, because you have NutSpec written properly, basically. So after this, our final step, our chapter will be auditing techniques. So I'll cover some types of audits there. Now we've imagined that we finished with our smart contract development. We ship it to the audit firm. What these audit guys will do to our smart contract, we'll try to explain that now. So there's several audit types first. So we have new audit. So new audit is when you have a new project, first-time project, and we are doing first-time audit. This is the longest one, of course, because the auditors need to understand your protocol, your project, with documentation, by interviewing you, what you're doing here, what's your idea, etc. Then they need to get familiar with the code base, and so on and so forth. Then there's so-called repeat audit. So auditing company already did audit for this project, but in the meantime, you implement some new features, for example, V2, version 2 of your protocol, and this is another audit, but it's much faster. Then fix audit. So after a new audit, the auditing company will probably find some bugs and vulnerabilities and will notice you, and then will return the project back to you to fix those bugs. And then the fix audit will just review those fixes from the prior audit or audits, and it's a faster one. Then retainer audit is basically when you're constantly reviewing project updates. It's not so common. And incident audit is basically when there's an exploit. So it's kind of different than the war room. So war room is when the exploit is happening and you try to secure funds, to secure users, to know even when multisig to restrict some orders whatsoever. And then after the war room, a couple days after, there's so-called incident audit, when basically the audited company and your team will review the exploit itself and try to learn something new from it. So first technique for auditing is basically so-called specification analysis. Auditors analyzes your project manually. Specification is basically what your project should do. So it's described in detail, like your idea with this project. For example, you're making DEX. In the specification, you'll write something like, hey, I want with this project to swap one token for another or multiple tokens for another or whatever. I'll do it by using these formulas. and so on and so forth. This is going to be my UI flow, something like that. So the pure specification, and the auditor needs to read it manually and to analyze manually. The second type is documentation analysis. So documentation, again, it's been doing manually, but basically the auditor will be probably read your documentation the same as you're probably reading documentation of other protocols as well. Function names, signatures, function parameters, storage variables, why they're named like they did, what's their purpose, and if you're using again NetSpec, this process will be much faster. And documentation is clear documentation. I know it's boring to write it, but it's really important. Then there's so-called static analysis. So now we have some tools. Basically, I mentioned static analysis at the beginning as an optional step before row to audit. So it's pretty simple to implement it by your own. So you can maybe try to run some scripts and see what static analyzer will tell you and maybe fix those to prevent some bugs. Basically, this is a technique of analyzing program properties without actually executing a program. So it's going to basically read your source code. And as I said, maybe it will find a string with TX origin, and it will warn you, here you're using TX origin. Maybe the safer approach is to use message.sender. And that's it. It won't actually execute your smart contract. So there's two common tools, Slither and Mythril. So the first one analyzes solidity code. So basically analyzes the TX origin. It can read it like a string. And then the Mythril analyzes EVM bytecode. So it basically compiled the solidity code and then analyzed the bytecode itself. So on a EVM level itself. Next up, property-based testing, also known as fuzz testing or fuzzing. It's basically a really common way to do it now, actually, as a part of your standard testing suite, because it's very powerful. So basically, fuzzers provide huge amount of random and unexpected inputs to your smart contract functions in order to break them. So what's breaking? It's a crash, it's unclocked exceptions, memory leaks, and so on and so forth. So some common tools which you can Google for fuzzing are Echidna. So Echidna can be easily used using some Docker images. We used Echidna in Hardhat Starter Kit, so maybe you can see it there. Then Foundry has built-in fuzzer. When you're writing tests in Solidity, it automatically runs the fuzzer itself. So you check our Foundry Starter Kit. And Harvey is another property-based testing tool. Then is so-called symbolic analysis. So your auditor will perform symbolic analysis, and it's basically a technique of checking for program correctness by using symbolic inputs to represent set of states and transitions formulated in some precise mathematical language. The most common tool for this purpose is Manticore. And I also listed symbolic analysis under static analysis as an optional step before auditing, because Manticore is also pretty easy and straightforward to use. So maybe you can perform symbolic analysis by yourself, just by running a script. Then there's so-called formal verification. So formal verification aims to detect complex bugs which are hard to detect manually or using simpler automated tools. Basically, static analysis or symbolic analysis or simple unit tests cannot caught these complex bugs. So basically, formal verification is here to do this. We usually don't write formal verification when we are writing our set of tests during the development phase, but auditors will perform formal verifications pretty often. So basically, formal verifications prove that smart contract satisfies a formal specification of its behavior. So formal specification is the first thing that the auditor will read manually. So it's what your project should or supposed to do, and then write a set of formal verification tests to prove those theories from that document. So some common tools are Works and Key EVM. This is a code snippet from the first tool, how you can basically create a property. So this is like a simple example for ERC20 tokens. So you always want to have the exact same number of decimal places. And this is how you can write a formal verification test. Also, I haven't mentioned in best practices, but I remember that now. So not all of the tokens has 18 decimals. Some of them have 6 decimals. Some of them have like 20 decimals, 12 decimals. But there's like someone with 24 decimals. And you need to also take care of that as well. So either by token lists or like with implementation and additional checks inside your smart contract as well to check for decimal places. And finally, the very last step after all of these tools and techniques and tests and everything is the so-called manual analysis. So auditors, like human manual editors, analyze is basically when an auditor itself, like a human being, will read and go through code base itself by his own or by his team, discussing with the team, because a human eye can caught something that these tools can't. And this is where great auditors and security experts distinguish themselves from the regular ones. Basically, you need to manually go through code trying to find vulnerabilities and bugs. Maybe be creative, like a white hackers try to break something. There's like two possible scenarios that can happen during manual analysis. So first one is you can find false negatives, and you can also find false positives. So false negatives is that some missed findings that should have indicated the presence of the vulnerabilities, which are in fact are not reported at all. So false negative is where there is a vulnerability in the smart contract, but it's not reported by tests, by tools, by formal verification, by fuzzing whatsoever. So there's a vulnerability, but no one caught it. And false positives are quite the opposite. So they are findings which indicate the presence of the vulnerabilities, but which in fact are not vulnerabilities. So your tools reported that there is a vulnerability, but in fact it isn't. So yeah, this is basically it. And this is the end of our workshop. So I'll just quickly do a Q&A session here. If you have some additional questions, feel free to write it in the YouTube chat. It would be great, a session using some of these tools on a real case. Yeah, agree. Maybe we can prepare something for upcoming hackathon or next hackathon or some YouTube video. We'll see. That's a great suggestion. But basically, during this Q&A session as well, feel free to scan this QR code because your feedback is really important to us. Because we can also, there's a link in the chat. Basically, we can see what we can do better, where we can improve that. Maybe you liked it, so also thumbs up is always nice. But basically, we're trying to make these sessions for you guys to find it useful. It's basically to not waste your time with some boring stuff. So that's why we prepared this advanced topic for you. I hope you like it. I hope you enjoy it. I hope you find it useful. Yeah. So okay, there we have one question. Thank you for the nice word, by the way, guys. For the people that are trying to become auditors, it is better to learn Hardhat or Brownie. Basically, it's, in my mind, that's just my opinion. The most important skill is to know how you can read Solidity, because you can master Hardhat or Brownie or any other framework later, because they're just for writing tests. And if there's like a project with good test cases, then you're probably not going to test suite. Sorry, they're probably not going to write some additional tests. But it's really important that you can know how to read Solidity or Viper or whatever the language is, because you can caught some unexpected bugs and behaviors potentially. Is there a standard? Is there a standard or Open Zeppelin module for testing, like checking your send address is burner address, or Audit should handle this? Yeah, basically there's no standard module or modifier. you'll need to write your modifier. So it's pretty simple. Just require that address is not address 0, and write it in the modifier, and then like pass that modifier to your functions, and that's it. Like I'm not aware that OpenZeppelin has this module. Thanks for the answer info. Yeah, glad to hear that. Securium have a great set of YouTube videos. Yes, I highly recommend you to go to Securium. I hope I pronounced that well. Their YouTube channel, because they're basically a course for smart contract edits, and they have great materials. Are you aware of any fuzzing tools that can be used with Brownie? Yeah, all of this. I think Echidna can. Actually, I'm sure that Echidna can, because Echidna can be run inside a Docker container, or you can install it as a CLI tool. So it's kind of like doesn't rely on specific framework. So just you need to set up it properly. That can be a time-consuming process, but I think Echidna will be good for Brownie. Was a great session. Yeah, thank you. Which tests should be included in the final repo? All of them. So unit test, integration test, whatever test you have, include them. That's it. Yeah. Greetings from Brazil. Yeah, say hi to Brazil. So understanding Solidity and mastering the additive tools is the best route for auditors. Yes. In my opinion, yes. Thank you for all. Yeah, thank you. At what stage of project should auditing be included? At the last step. So after you finish with your tests, with your optimizations, with static analysis whatsoever, you're like maybe test that on some test net, like privately. At the end, you'll reach out for audit company. Thank you. Yeah, thank you. Are modifiers best for updating state? If no, kindly advise how best to update the state of a transaction. So modifiers shouldn't update state. So modifiers should not have some complex logic or whatsoever. Modifiers should just have maybe a simple require statement, or maybe some if-else with reverse statements, basically to return true or false, and that's it. Modifiers are a way to check inputs of your smart contract for your smart contract functions, and not to perform any state change. So if you want to update the state of a transaction, as you wrote here, the implementation is following check effects interaction pattern, the second stage. So first you'll check inputs with your modifiers, and then you will update state. How much time we should include for auditing and the recommended fixes before planning the release dates? That's actually a good question, because it's basically when you find an auditing company, you'll negotiate with them like the terms, time frames and everything. And I think the best way is to communicate with them. So after you can always say something like coming soon, but I think after the fix auditing, so the first audit, and they will probably find something, and then you fix those bugs, and after that fix audit, I think you're good to go. So it really depends of how complex your project is, and because they need time to perform audit, basically. Do you know of any audit report templates? So yeah, there are several audit firms. I can maybe paste that on my Twitter, because one audit firm do something like info, low severity, medium severity, high severity, and there's like another audit firm does like a matrix, so low, medium, high, like a 3.3 matrix. Another auditing company do, I think, 7 stages of this. So it's basically up to a company itself. I can maybe create some simple thread to collect all of that info. And yeah, I'll probably do that tomorrow. Yeah, so Andre_dev on Twitter. And yeah, because I don't know like from my head at this moment, sorry. Are there any other security challenges out there, like damn vulnerable DeFi or Ethernaut? Yeah, so capture the flag is the third one. So damn vulnerable DeFi, Ethernaut, capture the flag, and also I think Paradigm released their capture the flag version I don't know when, but I think they release it. I saw it somewhere on Twitter. So that 3 or 4 will be okay, I think. Okay, I can see there's no more questions. Thank you guys once again for joining this session. I know it was a long one, maybe exhaustive one because there wasn't a code along, just a pure theory, but I really enjoyed it, and I hope you, as I said, you found it useful. Thank you very much.